So number 20, let me change to a different ink. A carbonyl compound X will react with HCN in the presence of NaCN. So we are looking at nucleophilic addition reaction, one of your key case study mechanism. Compound X does not react with phalanx. So phalanx is a test for aldehyde, so no positive result mean X is ketone. So it's only aldehyde and ketones that has the carbonyl that can undergo this nucleophilic addition reaction. If it does not react with phalanx, it must be ketone. Alright, so butanyl and propanol is aldehyde, and that means we can cross A and C out. And the next important information is the final compound has an MR of 85. If I just draw out butanone, so that is butanone. If I undergo HCN, well, actually HCN is a reactant, so I shouldn't put it on top of the arrow because it's a reactant. It's an addition, so there's a OH and there's a CN. The H goes to the oxygen, the CN adds onto there, you have lost the carbon-oxygen double bond. This is a C1, 2, 3, 4, 5. This is C5, H, 1, 2, 3, 4. There's no hydrogen there because carbon form 4 bond. 5, 6, 7, 8, 9. 1 oxygen, 1 nitrogen. So you can work out the MR. 12 times 5 plus 9 plus 16 plus 14. That is 99. And that is, well, 99 for the product, which is, so not for butanone, but for the final product, yeah? So that is incorrect, so it has to be D. And when you think about propanone and butanone, okay, D, but I can't even write D properly. I mean, you can work it out, but the idea is the same. You already crossed out the other possibility that it was wrong. Okay, so that means you're only left with one option, which is that. And you know you have one lesser CH2, so minus CH2, which is 14, the MR. So 99 minus 14 is 85, because you have one lesser carbon, minus CH2, alright? So minus 14 is 85, and there's your MR of 85. Question 21, you have geraniol and linalool. So you found them in flower fragrances. You want to know which statement is correct. So if we count the number of carbon first, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon there. Let's count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 carbon there. There is one OH. There's one OH and there's one OH. There is one double bond and two double bond. One double bond and two double bond. One double bond and two double bond. So you can see that they are isomers of each other. But what is different? Your double bond, what is different? So find the longest carbon chain, I guess. Find the longest carbon chain. If there is 1, 2, 3, 4, 5, 6, 7, 8. Then there's your 1, 2, 3, 4, 5, 6, 7, 8. And well, your OH is at carbon 1. Your OH is at carbon 3. So this is to do with position. This is definitely to do with position. Okay, because your 6, 7 alkene is still there. Your 1, 2 alkene has also changed to 2 and 3. So that is definitely position. Alright? Yeah, definitely positional isomers. Okay, so not only has your OH position changed, but your alkene has changed from 1, 2 to between 2 and 3. Number 22, you want to show the initiation step of this methane and chlorine. So this is your free radical substitution. That's just in the presence of UV light. If you show the mechanism, you will show them like that to show single-headed arrow, to show the flow of 1 electrons, to show homolytic fission. This is one of the key definitions under introductory organic chemistry, and stated in the syllabus, something you must be able to define as well. 23. So you have aqueous sodium hydroxide. You react it with halogenal alkane. So this is 1 bromopropane, so it's just 3 carbon. And then you got bromine. This is a primary halogenal alkane because the carbon with the halogen is bonded to one other carbon. You react it with the NaOH. So the OH minus attack the delta plus carbon and then kick out the delta minus bromine, and then you will get that and you will get NaBr. This is a classic SN2 mechanism because you have a primary halogenal alkane. So the first step in that mechanism is going to be a curly arrow from the lone pair of the hydroxide, okay, attacking the carbon delta plus from the lone pair of OH minus to the carbon delta plus. Okay, so that's correct. And because this is an SN2 mechanism, okay, it doesn't go via homolytic, it is actually heterolytic fission. I just mentioned earlier, right? This is the definition you got to know. If you don't know this definition, how do you expect you'll be able to do this question when they ask you something on homolytic and you can't differentiate with heterolytic fission? This bit here, C, is for SN1 mechanism. When you have a SN1 mechanism, you have a CH3, for example, you have tertiary halogenal alkane. So definitely not for this. You will just have heterolytic fission, breaking the carbon-bromine bond, having the 2 electrons moving to the bromine, not even to the carbon. So that's actually even incorrect. Okay, incorrect for SN1 or SN2. Okay. Yeah, okay, so A is the only possible correct answer there. 24, this is a calculation question. So you have ethanol, you have aqueous acidified dichromate, so that is chromium plus 6, that is your orange color oxidizing agent. You boil it under reflux, so you don't just heat and distill immediately. So the organic product collected by distillation is after you reflux it. So that organic product is actually carboxylic acid, yeah. So, but your yield is only 75%. Here you have 2 carbon, 2 carbon. Here you have 2 carbon, 2 carbon forming 2 carbon. The mole will be 1 mole of this, give you 1 mole of this, because 2 carbon give you 2 carbon acid, alright? But you have 75.0% yield. So what does that mean? That means the mole of the acid actually over the mole of the alcohol, it's not 1:1. 1 should give you 1, but you only get 75% yield. So 1 mole will give you 1 times 75 over 100, which is 0.75, because you only get 75% yield. 1 mole should give you 1 mole, but you only get 75% yield, so you only get 75% out of whatever you should expect to get. All right, so I can have that equation. Okay, I can have that equation, and I really run out of space here. Maybe I can just put it down there. That's not good. Okay, I just put it up here. All right, never mind. So usually I'll have another equation on the right to represent the actual amount of the acid and the alcohol. I use 2.76 grams of the alcohol. So if I work out the MR, this is C2H6O. So the MR is 12 times 2 plus 6 times 1 plus 16. That's 46. This is C2H34 and O2. So the MR of C2H4O2 is 12 times 2 plus 4 plus 16 times 2. That's 60. So I will expect to get 0.75 times 1 over 1. On the top is the mole of the acid. I want the mass of the carboxylic acid. So I will have the mass of the carboxylic acid divided by 60, because this is the mass of the carboxylic acid divided by 60, which is the molar mass of the carboxylic acid. At the bottom will be the mole of the ethanol. So I use 2.76. So it's 2.76 divided by 46. I reserve the top bit for the carboxylic acid. I only get 75% of it, which will give me the mass of the acid divided by the molar mass of the acid. At the bottom, I reserve it for molar ethanol. Started with 1 mole from the stoichiometric equation, which will give me 75% of 1 mole of the product. In actuality, I use 2.76 gram that divided by the molar mass of the alcohol, the ethanol. Rearrange your equation. So a bit of algebra there. I am really running out of space. The mass of the carboxylic acid is equal to 0.75 times 2.76 over 46 times 60. Okay, I'm not sure if you can see on the screen. I move all of these up here, multiply by 0.75, and then this over 60 equal to all of that. I move the 60 up there. So 0.75 times 2.76 divided by 46 times 60. Do it in 2 steps if you can't see it in 1 step. Whatever it takes in order for you to rearrange this equation, but do it fast because you don't have much time in the exam. Yeah. So the 75% yield is probably something that will catch a lot of students out. The 1:1 is not well understood because they don't really know that 2 carbon give you 2 carbon. You can balance the equation with obviously with the use of square bracket oxygen to represent the oxidizing agent, but we are interested simply in the stoichiometry, something we know, something we don't know. Okay, and obviously the 75% is something that will have a lot of students stumped and confused unless you specifically understand mole concept. Okay, you can see more example of this kind of question in my topical playlist on the MCQs on topic 1, which is to do with mole calculations. Alright, question 25. So you have compound X, single pure optical isomer. You use concentrated H2SO4, concentrated H2SO4. So these are alcohol. So consulfuric acid will involve elimination of H2O. Okay, but you only get one organic product. So we need to say you have a symmetrical alcohol. Okay, we are looking at symmetrical alcohol. What do I mean by that? I mean here you have CH2, which I've shown with 1 color. So what you can do is you can remove the OH or any of this H, but removing this H is different from removing this H, because if you see the symmetry there, this part of the molecule has a extra CH3 here. This part of the molecule has no extra CH3 here. So actually removing this hydrogen color in blue is different from removing this hydrogen in green. If I show you the example, so this will give you that, and it will give you that, and the other one will give you the other one in green will give you that, and that. Are they the same or are they different? Actually, we want the lowest number for our alkene, right? We always want the lowest number for our alkene, all right? So if we have 1, 2, 3, 4, 5, 6, we want the lowest number for our alkene. Okay, so 1, 2, 3, 4, 5, 6. So here you can see I could have gone the other way, but I will have higher number for my branch group. This will be the lowest number for alkene, lowest number for branch group. Branch group at 3 and 4, branch group at 3 and 4, they are the same. So actually A might be the answer because these two are the same. So the one in green and the one in blue are the same. That's strange. Okay, never mind. So A could be the answer. Let me check B very quickly. So you have a H there, and you also have a H there, which I should probably use a different color. Okay, so you can get the one in green, which is that, and that, and you can also get the one in blue, which is that, and that. That and that are different. Totally different, okay, because this is a double bond not next to the alkyl. These are 2 different products, so that is definitely wrong. Okay, so if I start with the next one, so I have a H there, and I also could have a H there. So what I could get is, I could get that and that and that, and then the one in brown would give me that and that. So there are two different products again, so that is incorrect. And lastly, I should probably use a different color one. Lastly, I have the OH there, that is on this carbon. So I'm looking at this hydrogen. So there's no other hydrogen. There's no other hydrogen for me to do. There's only this hydrogen. So really, the only product that I get is this, because there's no other hydrogen on the next carbon. This is the only one. So again, I'm skeptical about this. I'm really skeptical about this. Have I done something wrong? Let me just double check to see if I've done something. I know. You see, I definitely have done something wrong, you see. If I remove the blue one, the H and the OH, my double bond would be there and not there. You see, very easy to make mistakes. I was wondering like, how come it was that, alright? So I was wrong earlier, and it turned out that this is different from this, because then my numbering system would be different. Remember, we want to minimize the number on the alkene. We also want to minimize the number on the branching. So the alkene is 1 and 1, but your branching is 3, 4. Your branching is 4, 5. So there are two different products, okay? And here you only have one product. So really we are looking at D. And as you could see, I have made a mess. I've really made a mess. Imagine drawing this with display. Okay, I challenge you, drawing this with display. I challenge you for MCQ paper or for structure paper. No way you will be able to get to the answer in like a few minutes, yeah? Okay, try not to guess the answer as well. So get your hands dirty. Start by drawing and convincing yourself, yeah? So question 26, you have 2 bromo, 2 methyl propane. So propane, 1, 2, 3, 2 methyl, 1 there's 2 methyl, and then you have a bromine at position 2 as well. This is a tertiary halogenal alkane because the carbon with the halogen is bonded to 3 other carbon. So really we are looking at SN1 because it's a tertiary halogenal alkane. So there's delta minus, there's delta plus. The first step will involve the carbon bromine breaking. This is the red determining step, or it's a slow step. You will get a tertiary carbocation. You will get the nucleophile in the balance equation. So this thing is balanced by the inductive effect. Inductive effect has been covered in the AS syllabus. You can check my topical playlist on electrophilic addition that is under hydrocarbon. I think I cover specifically what this inductive effect is all about. And here we have 3 electron donating groups, the alkyl groups. They can stabilize the carbocation by the inductive effect of the methyl group because they are electron donating. So the electron donating, they will stabilize the plus charge there, SN1 and that, okay? So yeah, it's definitely not SN2 because of the presence of this second tertiary carbocation that is only possible as a result of this step from tertiary halogenal alkane. Question 27. So we have that 2,4-DNPH. It's actually a benzene ring. It's connected to NH. It's connected to NH2. So that bit is the hydrazine. Okay. And you have position 1 and position 2. You have nitro. Nitro is the NO2. You have 2 of them. That's why it's called dinitro. You have them at position 2 and 4. 2,4 dinitro. Phenyl. Phenyl is the benzene ring. Hydrazine. Okay. So many of these reactions need to be heated before reaction occurs. Which one occurs at a good rate? I can tell you the 2,4-DNPH with ketone or aldehyde occurs at room temperature. This one gives you the orange PPT, which is also crystalline. Okay, so that happens really well at room temperature. It happens instantly. This reaction is called condensation. So a lot of students don't even know how to write the equation. You kick out the H2O because this loses the O, this loses the H2N, the H2 from the N2. So what you get is you maintain the ketone backbone, but you lose the oxygen. Now you have the nitrogen. This nitrogen comes from here, and you just complete the rest of it. There you go. There is the 2,4-DNPH fragment. You have lost the H2 from the NH2. You have lost the oxygen from the ketone. This is the orange color precipitate. Okay. The rest of them, this one is a cracking, so you need high temperature. The next one is a nucleophilic substitution. You need NH3, you need concentrated NH3 in ethanol. You also need to heat under pressure. You heat it in seal tube. Okay. And then the next one is you need to replace the OH with Br. Typically, this is not how we would do it, but then this could be done, but you need to reflux it. Usually we would use HBr instead of KBr, alright? But D is the one that will obviously happen at room temperature. 28. A carboxylic acid has no possible chain isomer. So chain isomer is a branch versus straight chain kind of thing, yeah? So that comes under structural isomerism. It reacts with an alcohol Q that has one positional isomer. Okay, so two important information there. The carboxylic acid has no chain isomer, but the Q has only one position. Position mean like 1 chlorobutane, 2 chlorobutane, something like that, yeah? If you think about the ester that could be formed, if I think about the carboxylic acid, so this is a 3 carbon, this is a 4 carbon acid, because the O8 is the acid. This is a 2 carbon acid. This is a 5 carbon acid. Okay, if I have 2 carbon, there is no chain isomer. Okay, if I have 3 carbon, I cannot have chain isomer as well. Chain isomer means I can branch it out. If I have 2 carbon, I also do not have chain isomer. So 2 carbon and 3 carbon acid is fine. How about 4 carbon? When I have 4 carbon, then what I could have is, I could also have this. This is called a chain isomer because now I have 3 straight chain and I have 1 branch out. This is a chain isomer of this. You can't get this here because how are you going to branch it out? So these are the 2 possible compound, the acid for P, but not 4 carbon, alright? So 4 carbon, these are chain isomer. So we are looking at 2 carbon and 3 carbon acid. So 2 carbon acid and 3 carbon acid, so I can cross out 4 carbon acid and 5 carbon acid. Next up, I'm looking at the alcohol. 1 position isomer. So we are just looking at 5 carbon alcohol, or we're looking at 4 carbon alcohol. Always start with the simplest one first, the shortest chain. If I start with 4 carbon alcohol, so there's 1, 2, 3, 4. I'm looking at position, so I don't care about chain now. I'm looking at position. That has only 1 position. So there is butane 1O. This is butane 2O. Okay, so that is butane 1O. And you cannot have butane 3O because if you put the OH there, you want the lowest number, then you get back 1, 2, 3, 4, it will be the same. So this one has 2 position isomer. I must have done something wrong. Oh gosh, okay. That has only 1 positional isomer. I guess you can call, in addition to this butyl, the butyl that could refer to just the straight chain. In addition to this, there's only 1 other isomer. There's only 1 other positional isomer. Okay, so I think that could be the way we could rationalize it. Otherwise, I cannot imagine the answer being C, because when you have pentyl ethanoate, you will have pentanol. If I use a different color, black for example, if I have pentanol, there's 1, 2, 3, 4, 5. You could have 1, 2, 3, 4, 5. You could have OH like that. You could also have OH like that. Pentane 1O, pentane 2O, pentane 3O. You have 2 other positional isomers. Altogether you have 3. So it can't be pentyl, it can't be the pentanol. Okay, so it's not C. So we are looking at option A really. Okay.